Okay, so welcome back. Next up, we have Paulo Oliva, who's a long-time collaborator of the team, and who's going to talk to us about higher order game theory. Please.
Fantastic, thank you very much. So in a meeting like this with both theorems, definitions, but I think in an event like this, which is a 6th birthday celebration, I think what we love the most is story. And as it happens, I've known Martin since, I think, 2002, probably when Martin came to give a talk in Aarhus, in Denmark, where I was doing a PhD. Then I exchanged some emails. I was looking through my emails to find when was the first time we started talking about research. I asked Martin for some references on real numbers, computable real numbers, because I joined the project in Queen Mary on verification of continuous systems, and I thought we need to deal with real numbers, computable real numbers. And Martin, in 2004, gave me some references. And then there was nothing until we met, we were both invited speakers in Wallach in 2007 in Rio. I think that's when we really started collaborating, because around that time, Martin was talking about his work on selection functions and searchable sets and exhaustible sets and so on. And when Martin gave his talk on this combination of selection functions and how they kind of witness that the product of searchable sets is searchable, then I thought, wait a minute, that construction seems to be very similar to the construction of Spector from many years before, when he was dealing with trying to find the witness for the computational interpretation of countable choice, the direct interpretation of countable choice. Now, maybe not everybody here would be familiar with these works that I'm mentioning, so I'll just say that at that time, what Martin called the selection function was something that, giving a subset of X, would find a point in X if that subset of X was non-empty. So you could say it was something that said, if there is an X in X, such that P of X holds for some predicate P, then P of that epsilon of P would hold. So that's what Martin called a searchable set. So it's a set that has a computable selection function. So if you give me a subset of that space X, and I'm able to find a point in that subset, if the subset is non-empty, then that space is searchable. And what Martin was trying to do was to find computable analogs to topological notions. Like, for instance, we know that computable functions are kind of related to continuous functions. Open sets are related to RE sets, and so on. And at that time, that dictionary between computability theory and topology was missing the notion of compactness. So there was this notion of compactness in topology, but there wasn't a corresponding notion in computability theory. And Martin came up with this notion of an exhaustible set or a searchable set as a set that has a computable selection function. Now, in topology, you have Tychonov's theorem that says that the product, even the countable product of compact sets is compact. So Martin had to come up with a way of taking a sequence of selection functions that witness that each space xi was searchable to show that the product space pi I xi was also searchable. And that was what he called the product of selection functions at the time, which showed how to combine countable many of those into a search operator for the counter space. Okay. And it's really impressive because this counter space, as we know, is infinite. And Martin went about talking how he could search infinite spaces, and everybody thought was really, really amazing that this is actually possible.
Can I interrupt?
Sorry?
Can I interrupt? 1 second. Actually, Ulrich Berger, who is here, was the first person to come up with the searchability of the Cantor space.
Yeah, the searchability of the Cantor space was Ulrich Berger.
Yes.
And maybe we'll talk about this. But this idea of a searchable space and the relation to compactness, I think, was Martin's contribution. So in the direct interpretation, what you have is something quite similar. You have this non-counterexample function. So you think of this as a function taking witnesses to refutations, then a witness works. And then you think of this operation as refuting that refutation function is a refutation function. So Kreisel called this the no counterexample interpretation. It's like saying that you give me a counterexample function that refutes my witnesses, then I will refute that counterexample function. Okay? But it's exactly, well, not exactly, more or less the same kind of type. And as it turns out, Spector's interpretation of countable choice was also putting a sequence of those together in exactly the same ways that Martin was doing and Rick Berger did with the Cantor space. So we thought, what is kind of common between these constructions? And that's where we start talking, I think, in 2007. But nothing really kind of, we didn't make much progress until, I would say, April 2009, when I got this email from Martin with an attachment called eureka.pdf. And this is in Portuguese, so this is the English translation, where Martin said, I think I found a specification of the product function. This is the product that we were looking at, which generalizes both the dialectic thing and the product of selection functions in his sense. And then he stated some claim that this is what is really realizing. And that's what led us to really work intensively on this and eventually come up with this idea that maybe there is a more general construction that subsumes both of those. So just a few months later, then Martin came to Queen Mary to give a talk. And he already described in his abstract that I will show that this product function that he was describing as his kind of fast links paper turns out to be a form of bar recursion that is, it has a specification much more general than the one given in that paper. And for example, it computes winning strategies for sequential games. So what happened was that in order to kind of see how these two things are really the same, we had to find this more general notion and generalize essentially game theory so that these two things are instances of this general construction. And that's what I will try to very briefly sketch in this talk. So this was our first paper back in 2010, where we presented these high order games, where you have not replacing essentially what the game theorists use as argmax, maximizing players, for more general selection functions, and also, as I mentioned, these quantifiers. Okay? So it's really a tale of these two monads. You have the continuation monad that people had studied for many years before, but what these selection functions were, they were really elements of this selection monad. So this monadic structure of these selection functions was really what was behind this product construction. And these are not just monads, so they have the eta and the beta, but they also have the tensor, because they are strong monads. So there are two tensors, but one of them is the one we use, where you sequence things from the left, in some sense. And so this is how you can think of this as a way of putting two quantifiers together, like when you sequence a for O and exist. So you say for OX, there exists a Y, something happens. Both for O and exist are, you think of them as continuation operators, if you think of the R as the booleans. Whereas the selection function is almost like Hubert's epsilon term. It's something that giving a predicate, X arrow R, it picks the witness, it picks X that satisfies the predicate. But that's also a strong monad, so that it also has this product operation. And this product operation was really the construction behind both the searchability of the contour space, the construction behind Tikhonov's theorem, and behind spectral Barry recursion. So it was exactly this idea that you can compose two selection functions on spaces x and y to a selection function on the product space x times y. Okay? So not only that, so you have these two monads, but there is a monad morphism between them. So you can always go from the selection function to the corresponding quantifier. So that's how Hilbert defined quantifiers from the epsilon terms. So you can define exist x p of x as p applied to the selection function applied to p. So selection functions define quantifiers. So you can always go from selection function to quantifiers. But you can also say that multiple selection functions can define the same quantifier. So it's a kind of a one-to-many relationship. And in fact, what we used in that paper was this idea that you can say that a selection function attains a quantifier if that relation holds. Okay? So you could say argmax attains the max. As if you think of the R here now as the real numbers, this could be max, maximizing a function. And the fact that the max of a function is exactly the function applied to the Rmax of the function is what shows that Rmax, in some sense, attains the max quantifier. But you can also think of R as being X itself. Okay? So if you think of R as being X itself, then actually these two types are the same. And phi and epsilon, examples of those are the fixed point operator. So the fixed point operator can be thought of as a quantifier and a selection function. And the fact that it is a fixed point operator is exactly saying that it attains itself. Because the fix of f being equal to f of the fix of f is what makes it a fixed point operator. So I think this, to me, was absolutely fascinating. That we were able, in some sense, to take quite different research areas, and we really had very complementary kind of background. I knew very little about topology and computability theory, and I hope I taught Martin a little bit of proof theory as well. But by working together and being open to each other's ideas, we were able to find this common kind of theory that generalizes these two problems. So eventually what we came up with was this. So we defined a high order game to be essentially a tuple with a type for the outcomes of the game, a sequence of types for each of the rounds in the game. So think of xi as the available moves at round I. And the Q here is the function that, given the sequence of moves, tells you what the outcome of the game is. Okay, so we think of this as the outcome function. And now, to completely describe the game, you have to describe what is the goal of the game. What are the players at each round trying to achieve? Okay, and in that case, what we use is the quantifier. So the quantifier tells you what the players are trying to achieve. And for instance, if these quantifiers are the existential quantifiers, then the players are trying to, and then in that case, Q here is just a formula on n Boolean variables. And what the players are trying to do is to find a satisfying assignment for that predicate. So this here is just satisfiability. Okay? If you replace the set of outcomes by n tuples of reals, and the Q as the payoff function that will tell at the end of the game how much each player got, then these quantifiers could be max with respect to the ith coordinates. So each player is trying to maximize their own payoff. If you replace R and X by, so if you replace R by X times Y, and you have two rounds, X times Y, then you could take phi here to be, again, the fixed point operators. And what this construction will do is exactly what's known in domain theory as Becky's lemma, where you have that if two spaces have fixed point operators, then the product space also has a fixed point operator. So there's exactly an instance of this as well. In our earlier papers, and even in our latest papers, we have been using the tic-tac-toe as a kind of an example where we can test ideas. And in this case, for instance, you can take the set of outcomes to be X wins, O wins, or it's a draw, so 3, minus 1 and 0. The X's at each round are the positions on the grid that you play, and Q decides the outcome of the game, given the sequence of moves. And now the players are just max and min, max and min, max and min, right? Alternating. So one player is trying to maximize and the other one is trying to minimize and so on. Now, the nice thing about this was that not only we could generalize, so the original kind of games in game theory, this phi here will always be max. Because you could say, well, going back to von Neumann, when von Neumann describes game theory, he said you can always think of players as maximizing players, because you can always change the ordering on the outcomes, and you can always see people as maximizing. And since then, that's all what people did, I would say, in game theory, is to think that we are maximizing agents. I think what we did here was to say, look, we can be more flexible and allow this to be any quantifier, not just max. And indeed, by doing this, you capture things that game theorists struggle with. For instance, in game theory, there is this paradox called the beauty contest paradox, where one of the contestants wants to vote for the winner. Okay, so you say, I don't care, I will vote for anyone as long as that person is going to be the winner. Okay, that exactly is phi being the fixed point operator. So you're trying to pick a move such that the outcome of the move is the one that you picked. Okay, so by generalizing the definition of a game this way, we are able to capture things that you can't really do with maximizing agents all the time. But not only that, we could define things like the optimal outcome of the game, and we could still define what an optimal strategy is. Because an optimal strategy, so sigma is an optimal strategy if at any point in the game, if you continue the game by following this strategy, you get an outcome, and if that outcome is the same as the best possible outcome, if you deviate from the strategy, then that strategy is optimal. Okay, so playing a strategy in which you are always achieving the best possible outcome, that's what the definition of an optimal strategy is. In game theory, they talk about no incentive to deviate from what you have played, so that they call it equilibrium. But that's what it is. It's just picking a sequence of moves, which essentially witnesses or validates the quantifier over all possible variations of that move. Okay? So we could generalize the notion of an optimal strategy, of an equilibrium, in the sequential game. So what we showed is that you don't need maximizing agents to do this. Now, the nice thing is that then with this kind of general notion of outcomes, moves, outcome functions, go functions as the quantifiers, and selection functions as the implementations of the go functions. So if a selection function, so if these quantifiers that describe the game are attainable in the sense that we have selection functions for them, then we can not only define the outcome of the game, but we can actually compute the optimal strategy by using the product of selection functions. Okay. So the product of the quantifiers will tell you what the best outcome of the game is. The product of the selection functions that attains those quantifiers will tell you what the actual the best play in the game is. Does that make sense? So this was what we did. So that product of selection functions, I would say, was as computing optimal strategies was the thing that kind of unified both of these work. So we could now think of the computation, this combination of selection functions to witness Tikhonov theorem and Spector's bar recursion as both computing optimal strategies in some sort of game. So that is what I want to say. We have been recently working with monadic extensions of this, so selection functions with monads that we introduced in 2017. And this so far has led to, I think, 12 papers, as I counted, and we're hoping that with these monadic selection functions and 20 years of kind of collaboration, almost, so I'm hoping that this will give us another 20 years ahead. So thank you very much, Martin.
Time for a few questions.
Yes, I saw you standing up, so I didn't want to take too much time. But one of the things I wanted to mention is that as soon as we started collaborating, I got an email from Martin saying, "Paulo, do you know about the Hardy-Littlewood rules on collaboration?" I don't know if you remember, Martin. And essentially, it says, so it was Hardy and Littlewood, they had this very productive collaboration. And the axioms were some things like it didn't matter whether what they wrote to each other was right or wrong. There was no obligation to reply. They should not even think about the same things. And to avoid any quarrels, all papers should be under their joint name, regardless of who contributed or something or nothing and so on. So I thought it was really interesting, and I remember that when I was preparing this. And because I think these rules are about, I think, respect, admiration to each other, and trust. I think that's what really exactly what I feel for Martin. Thank you very much.
And me too.